Exactly.
You can take the integral of one graph minus the integral of the other.
Okay, there we go. Lesson taught. I'm done. Ross just taught it. Okay. And for the benefit of Abby, who probably didn't hear that, who's listening to this and saying, what? Okay, let's actually go through the lesson, though. So what I was saying before I hit record is that lesson 60 is basically, it's a continuation of yesterday's lesson. Yesterday was, what was our official title? Area under a curve?
Yeah, but it was
Yeah.
or something.
Yeah, computing areas. The idea yesterday, it was area under a curve, but it was always area between the curve and the x-axis. That x-axis was always the other boundary. And if you think of what is the equation for the x-axis? Y equals 0. So even though we never talked about it, we really were doing the upper curve minus the lower curve, because the y-axis, the x-axis was my lower curve, but that's y equals 0. And there's nothing to subtract if it's 0. So when it's just find the area under a curve, then you're integrating that curve, because the x-axis is just 0 and you don't have to worry about it. What we're looking at today is finding the area between two curves. And if we're finding the area between two curves, you've got a couple of diagrams here. Notice on this left diagram, you've got f of x up top, g of x down below. And so this would be saying the integral from a to b of f of x minus g of x dx. Or what you heard me say, it's upper minus lower. You're integrating the upper curve minus the lower curve. If we look at this second diagram, you have to be careful, but if this, notice, where is f of x? It is right here, yes? And it is the upper curve up here. And so if this is my A and this is my B, then we're doing upper curve f of x minus lower curve g of x, and I'm finding the area in between those two curves. Now, if my A and B intervals are different, we might have a different story going on. Okay?
Is that a later lesson? Not changed.
Necessarily. We'll kind of include that today, I feel like. Okay, example 1. Here we go. You guys have the basic idea. I think you had the basic idea before I started today. So find the area. So what's your brain automatically saying?
Integral.
Integral. So find the area of the region between the graphs f of x equals x squared plus 2 and g of x equals negative x on the interval from 0 to 1. So they're specifically telling me an interval here. Like yesterday. Yesterday I said, okay, you need to graph, right? You need to graph because if it is something below the x-axis, it ends up being negative, doesn't it? And so that's why I said you need to graph it. You need to see if any of these areas go below the x-axis. Today we need to graph it to see which curve is on top. Because this general form up here says f of x minus g of x, as in f of x representing the upper curve in both cases. They give me f of x and g of x. Am I definitely saying that f of x is the upper curve here? That's not what it means. We're always going to do upper minus lower. Probably would have been better if these were named something other than f and g, so you had, so you don't think that way. Okay, let's see. Did you graph it? X squared plus 2? Parabola moved up 2. I'll get more specific with that if I need to, right? And I am going to label this on my graph that is f of x. Because that's kind of looking like it is going to be the upper curve, isn't it? G of x equals negative x.
It would be a negative slope, perfect diagonal, right?
Okay, it's our perfect diagonal line, but negative slope instead of positive slope. So that's going to go through 0, 0, and it's going to have a slope of negative 1. So you can go up 1 and left 1, or down 1 and right 1. And that is g of x. And we could get more specific with these graphs if we have to. And it says on the interval from 0 to 1. So 0 is represented by the origin, the y-axis. 1 is represented by this tick mark right here. And if you think about a vertical line there, do you see the area we are finding? Looks something like that, whatever that random shape is. Now as we go to do this, remember we're going to do upper minus lower as I set up my integral. So, and I mean, you could set it up as two integrals if you want, but it's not necessary. You'll notice right here, it's the integral of f minus g. If for some reason you feel like you need to do the integral of f minus the integral of g, that works. Okay, integral. What are my boundaries on this integral?
0.
0 to 1 because they told me so. And on a problem like this, they're going to have to tell you boundaries. There's nothing, there's no included space that's like sealed off or anything. They're going to have to tell you boundaries on a problem like this. So 0 to 1, which is my upper curve? F of x. So I'm going to, which is, so we're going to do x squared plus 2, which is our upper curve, minus, what's my lower curve? G of x, which is the negative x, and then dx. Are you okay with that setup? I mean, we have to start off with the easy ones, right? At some point, I would definitely say that minus a negative is plus, because that's just extra mess that is unnecessary. I just didn't do it to begin with because I don't want you to get some weird thought that, oh, we add them. No, subtracting. Okay. What's the integral of x squared? Okay. 1/3 x to the third, or if I switch it up today, write x cubed over 3, or you can write 1/3 x cubed, plus integral of 2x. Then I'm going to say it was minus negative x, so I'm going to say plus the integral of x, 1/2 x squared, or x squared over 2. Evaluated from 0 to 1. Okay, when I put 1 in, 1/3 plus 2 plus 1/2 minus, when I put 0 in, 0 plus 0 plus 0. You don't have to write 0 plus 0 plus 0, but that's just, you know, the visual. 1/3 plus 2 plus 1/2. Yep. So 2/6 and 3/6 is 5/6. So my brain went to 2 and 5/6. That was easiest for my brain because then I can easily go improper, which was 12 plus 5, 17/6. Although it wouldn't have been bad to say 2/6, 3/6, and 12/6. I just didn't. And of course, this is 17/6. Units squared. Okay, moving along. Find the area of the region completely bounded by the graphs of f of x equals 2 minus x squared and g of x equals x. Notice they don't give me boundary points here, do they? So it says bounded by the graphs, and notice it says in parentheses we have to find their intersection points because that's going to determine what boundaries we're using. Okay, what do you got for f? 2 minus x squared.
Upside down parabola with up to, right?
Upside down parabola, because it's negative x squared. The positive 2 means it went up 2. Debating how accurate do I want to, how accurate do I need to be here? And I guess what I'm saying at this point, we have to find some intersection points, yes? So as I set to do this, I mean, here's my vertex of my parabola. What do you know about a parabola, though? A basic parabola of x squared from that vertex is going to go normally over 1 up 1 both ways. In this case, we're going over 1 down 1. And if you want to go ahead and go a little bit more, the next set of pairs would be over 2 from the vertex down 4, over 2, down 4. And this was f of x. I thought it was kind of helpful to go ahead and put those points in now, since we're going to have to know intersection points. And let's see, g of x equals x. That's going to go through what? 0, 0, 1, 1. It's also going to go through -1, -1, and -2, -2. Have you seen why those parabola points were helpful? Because if you think about this as you go, I just pinpointed my intersection points along the way, didn't I? This intersection point here is 1, 1. This intersection point over here ended up being -2, -2. Okay. Where's the area I'm finding? Yep. Above the g of x, below f of x, in that little area there. What boundary values am I using? -2 and 1. Now, for the benefit of future, which -2 and which 1 am I using? The x. Because we are working in x's, we are integrating x variables, we are specifically using the x's. And that might matter on a future problem, right? So I want you to understand we're using the x coordinates as our boundaries there. Okay, shall we integrate? The integral from -2 to 1 of, what was my upper curve? Two minus x squared minus, what's my lower curve? X times dx. I feel like this integration might be a little familiar. So integral of 2 is 2x minus the integral of x squared, 1/3 x cubed, or x cubed over 3, minus the integral of x, which is 1/2 x squared, or x squared over 2, evaluated from -2 to 1. When I put numbers in, let's see. I'm going to put in my 1, 2, minus 1/3, minus 1/2. And I put that set in parentheses, and then minus, I'm going to put this set in parentheses. Now I'm putting in -2. So -4 minus -8/3 minus 2, if you will. You guys okay with that? You guys are all working ahead of me, so I kind of figure either that or you're following right along with me, one of the two. I will, if you didn't already, minus -8/3 was plus. So however you go from here, I mean, if we look at this first one, it's 12/6 minus 2/6 minus 3/6. So 12/6 minus 5/6, 7/6 in my first parentheses, I believe. And then, -4 plus 8, so we're going thirds. So -12/3 plus 8/3 minus 6/3. Or actually what I would have done is I would have said -4 and -2 is -6 is what I would have done. And -6 is -18/3 plus 8/3. Is it -10/3? So now I have 7/6 minus -10/3. So 7/6 plus 20/6. And I'm going to say 27/6. Barring I didn't make any killer mistakes here.
It took me a second to follow along with the second one because I did 6s on the second one.
Yeah. I tend to, like, if I see two whole numbers like that, I'll be like, oh, -4, -2, that's -6. And then I'll go for common denominator. But this is not the answer I have in my answer key. I just looked down. But this would be AP acceptable.
Because you could divide by 3.
27/6 divides by 3, and it's also 9/2. I didn't make any killer mistakes, although I did cringe for a moment. I was like, crud. Why? Oh. Because in my notes I have equals 27/6 equals 9/2, and 9/2 is what I have boxed. So that's the least of our worries at that
So
point.
you scared yourself for a second.
Half a second there, I was like, ooh. Okay. Ready for example 3? Find the area of the region between the graphs of f of x equals 2 minus x squared and g of x equals x on the interval 1 to 2. What? That's weird. And you know it's weird already because you're realizing this is the same graph. So this is the 1 to 2. This interval are x values. So here's 1 and here's 2. 1 is an intersection point, right? And 2 is just that right there. Okay? So that orange space goes with this example. I'm sorry, I'm lazy. I don't feel like we need to redraw the graph. Actually, it's a waste of time. Because you didn't realize that, or you just did.
I noticed it. I just
Okay. Yeah. How does that change things here?
changes what we're taking the area of.
Mm-hmm.
So it changes our bounds.
Okay. Changes our bounds, right? Instead of -2 to 1, we're now doing 1 to 2. What else does it change?
Now, x is the upper, right?
Did my upper and lower curve flip-flop? Because once it went through this intersection point right here at 1, 1, now g of x is on top and f of x is on bottom. So we're doing our g of x minus our f of x curve because what's on top has flip-flopped. Not only the boundaries, but so as I set this up, g of x was x, so it's going to be x minus, and then f of x is 2 minus x squared. So notice what I did here. I'm subtracting the quantity 2 minus x squared, so I put it in parentheses for official notice here. It's either that or you have to change your signs of both the 2 and the x squared right away. But you're subtracting that whole quantity. If you want, I'm going to rewrite it real quick. The integral from 1 to 2 of x minus 2 plus x squared dx. Does that work? And I think we're integrating some of the same stuff we've been integrating all period. There's good and bad to that, right? Okay, integral of x, 1/2 x squared, or x squared over 2, minus integral of 2, 2x, plus integral of x squared, 1/3 x cubed, or x cubed over 3, evaluated from 1 to 2. No negatives to plug in this time. Okay, I'm going to plug in 2, and when I plug in 2, I've got 2 minus 4 plus 8/3 minus, now I'm plugging in 1, 1/2 minus 2 plus 1/3. See, this is where Ross and I are going to disagree. I'm going to say 2 minus 4 is -2. And that's -6/3 plus 8/3. So I'm going to say 2/3. Minus 3/6 minus 12/6 plus 2/6. So I have 2/3 minus -7/6, which really becomes 4/6 plus 7/6, 11/6. And no reducing to catch me off guard this time. We have 1 or 2 on the back side. 2, dang it. I gotta get moving. I don't feel like I've been that slow today, but move along. Okay. Find the area of the region bounded by the graphs of y equals x squared and y equals 2x squared minus 4.
I feel like there's gonna be something wrong.
What'd you say?
I feel like there's gonna be something wrong.
I think it's just hard getting the graph correct, is what I think. What are you graphing here? 2 parabolas. So I think the wonky part, if you will, is just being able to figure out what parabola is doing what. Okay, whether you're graphing by hand or using the calculator. Y equals x squared. We know that one, right? I would be specific on your points here. So 0, 0, 1, 1, 2, 4. Okay. Got the easy one out of the way, right? 2x squared minus 4. Well, first of all, it takes the parabola and moves it down 4.
And then it stretches it, right?
It stretches it by 2. So when we normally go over 1, up 1,
We're gonna go up 1 over 2, right? Or up way around 1 up 2.
it's still over 1, but now we stretch it. So normally we go up 1. When you take that 1 and multiply it by 2, we're going to go up 2. So from here, I'm going to say over 1, up 2. Over 1, up 2. Normally I would go over 2, up 4 for my second point. So we're still going to go over 2, but when you take that 4 and you stretch it, you're going to multiply it by 2, so we're going to go up 8. Bless you. So I'm going to go from my vertex over 2 up 8, which just so happens to land on those points up there. Okay. And maybe I'll use a different. What happens is that second parabola I've drawn is skinnier. And so at those points 2, 4 and negative 2, 4, my parabolas cross. And now the wider parabola is outside and the skinnier parabola is inside. Okay, you got thoughts here?
So we have to use the intersection points, which
Okay.
we have now.
Okay, so it just said find the area. Did they give me an interval to work with? No, they did not. They've got to make us think. And so it's the area bounded. So it's going to be, I don't even know how to color this. It's going to be this area right here, isn't it? And so as we think what's the farthest left boundary and the farthest right boundary, we're using those points right there. What are those points?
-2, 2.
Okay. Negative 2, 4 and positive 2, 4. And we're going to use which values? The x's. See, now it matters. This is why I have to ask. Although the y's wouldn't make sense in this case. Anyway, it's going to be the same number. Okay, so the integral from negative 2 to 2. What's my upper curve? X squared. Minus, that means my lower curve is 2x squared minus 4. Okay. could clean this up before you integrate, and I would definitely encourage it. What do I mean we could clean it up before we integrate?
It'll end up being x squared minus 2x squared, so you just end up with minus x squared.
Yeah. Go ahead and clean it up so we can go from 3 terms to 2 terms. 1x squared minus 2x squared is going to be negative x squared, and then plus 4. So I'm integrating negative x squared plus 4. Integral of negative x squared is negative 1/3 x cubed, plus the integral of 4 is 4x. Evaluated from -2 to +2. I'm going to go ahead and plug my 2's in. Because I kind of get the impression you guys just prefer to just kind of do this part on your own. I had -8/3 plus 8, and now I'm going to have minus and positive 8/3 minus 8. So negative 8/3 plus 24/3 is going to be 16/3 minus, and it's going to be negative 16/3. So 16/3 plus 16/3, 32/3. I say that with a question in my voice because I have not looked at the answer key. Okay. I agree with myself. I got ahead of you guys on that one, didn't I?
I kept forgetting that you have to distribute like the negative at the very top, and so like the last like 2 problems we did, I'm like, how come I'm getting a different answer?
So it wasn't that I got ahead of you on that one, you were having to correct yourself.
Yeah.
That's what you're really saying. What's the last one say?
Yeah.
Utilizing the graphing calculator to find these areas a little easier. This one's, well, I probably shouldn't say it's impossible to do, but our intersection points are not going to be nice, neat, whole numbers. So, let's graph them. So y equals x to the 5th minus 4x squared plus 1, 2x squared minus 4. Zoom 6. I'm going to draw my graph here because I need something to point at and put all my information on. Notice it just says determine the area of the region bounded by the graphs. You guys all get it graphed? Okay. Graph should look like that lovely thing, doesn't it? You've got a parabola. That's nice, neatly, centered. And then you have this, I started to say cubic, I guess it's a quintic. But, I don't know, you might need to zoom in, although, now that I look at mine, I can see it pretty closely. And so realizing, it's going to go up here, it's going to go down here, don't exactly like my graph, but it gets the idea across. Determine the area bounded by these graphs. What do you see?
2 parts.
2 parts? because there's
The big chunk. The little nugget at the end.
okay, so we have the big chunk, got it, and the little nugget.
Those are the official terms.
those are the official Ross Cassidy terms for today. I'll take it.
If you don't like it, take it up with the manager.
I mean, it is the bigger portion and the smaller portion. That's about as official as I can get. I don't have anything official for this. Now, you're going to have to do some calculator work here, because what do I need to know?
The intersections.
You need to know the intersection points. So there are 3 points I have to know. I have to know this point right here. I have to know this point. And I have to know that point. And you can do that on your calculator using second calc and so like 4 or 5 down, maybe number 5. And then as you do that, the first question to ask you is first curve. So that can be y1, which is my blue curve. And then my second curve, make sure it says y2 up top, which that should be pretty easy. The guess matters because we have 3 different intersection points we have to find. And your guess determines which answer they're going to give you. You know, sometimes we ignore the guess and just hit enter. Don't do it. Or you might not get the 3 different points. Does that make sense? So if I want this one right here, I'm going to be right there and hit enter. Notice I have an intersection point. And I think I have these two 4 decimal points. So this one is -0.8670, comma, -2.4967. Repeat the process to find the other 2. Ooh, I like the next one.
Yeah, it's easy.
Did you guys get the next one? I didn't remember that and I didn't look, so. 1, -2. Third one's not nice. $1.5905, comma, 1.0594. Which values do I need? The x's. Yes, I wrote down the ordered pairs because I want you to understand them. But I'm going to circle the x's because I don't want to grab the wrong pairs. So, you know, really, as long as you know the x's, you're good. Be smart. If you got the same intersection point for 2 of these, realize your guess failed, right? You didn't get your guess in the correct area there. Okay. Was it the big chunk? Is that the first one? Okay. Big chunk. How do I do the area of the big chunk?
So it'll be the integral of that first x value, 2.8670. And you'll go to the next intersection, right? So the top will be 1.
Okay, so my boundaries, the -8.670 and the 1, because those are the boundaries on the left and right. Yes, I agree.
And then the quintic would be the upper value.
Okay, and this is where you have to be careful. Which is my upper curve? And at this point, it's this right here, yes? And that upper curve is the quintic. So that's going to be x to the 5th minus 4x squared plus 1. Notice I put that in parentheses which, I don't know, maybe you can get away without that one being in parentheses. Then we're going to subtract, and this other one has to be in parentheses, doesn't it? 2x squared minus 4. That's the big chunk. Now we need a little nugget. Okay, so we realize the little nugget's this guy over here, yes? And by the way, I wrote it with, we're adding, yes? We're adding this next integral because we're adding the two areas together. So for the little nugget, what are my boundaries?
It'd be 1 and then 1.
Yeah. The 1 is the small boundary. The 1.5905 is the upper boundary.
It's big on this one is the top and bottom flip, right?
Okay. And now, what is the upper boundary? Now the upper boundary is the parabola. So now I'm going to say, I'm going to put in parentheses, 2x squared minus 4 minus, the next set of parentheses is necessary, the quintic, the x to the 5th minus 4x squared plus 1 dx. And at this point, it's all about not hitting a wrong button on your calculator. But Maddie knows about her delete button now. Shively knows about his insert button
I
now.
actually did that earlier.
Okay.
Very proud of myself.
And I don't know if anyone caught on. Technically, we have these typed in y1 and y2 already.
I use that on most of my experiments.
So technically, for me, whoops, my quintic is y1, my parabola is y2. And so I could use those in my shortcuts because on the graph I have y1. The parabola is y2, and I can find that y1, y2 up in my alpha, I think it's like over alpha F4 or so. Abby, if you want to know what I'm talking about and you're confused, ask when you get back, okay?
Yay. I was really hoping that.
And you know you got it right. You typed it in right if your answer matches mine. .6905 is 4 decimal places. So I guess 6.691 would be 3 decimal places. Okay? If you didn't get it to work out right on your calculator, you just typed something wrong. I mean, master it now though, right? Learn how to do it now. It sounds like some of the shortcuts we talked about yesterday are helping in bits and pieces, so.